Part E. You know what I might do on this one to get started? Let's go. I think I'm going to distribute the 1/2 just so I can focus it on a piece by piece. So 1/2 cosecant squared x minus 1/2 cosecant x cotangent x. So I'm now looking at the integral of that. So if we take it piece by piece, say our variable is x, so I'm going to pull off 1/2. All right, so now we need to take the integral of cosecant squared. Well, according to our rules, the integral of cosecant squared is you would go to the angle. The angle in this case is just x. If there was a number in front, it would be just -1 over the number. But we'll just leave that in there just so we can get used to the formula for just a second. And then it's times cotangent of that angle. Okay, so that'll take care of the first part. Pull off the 1/2 for a second, and then the integral of cosecant x cotangent x. Again, if there was a number attached, it would be -1 over whatever that number was, and then cosecant of the angle, and then all of that plus c. Okay, so the indefinite integral would be -1/2 cotangent of x plus 1/2 cosecant x, and then plus c. And that right there is our answer. Okay, why don't we start right here and try it one more time. Let's check this. Like if I asked you to take the derivative of this guy right here, we would pull off the -1/2. And what is the derivative of cotangent? Well, the derivative of cotangent would be a negative cosecant squared x. And then if I pulled off the 1/2, what's the derivative of cosecant? Well, the derivative of cosecant is a negative cosecant x cotangent x. And the derivative of a c would just be 0. So a -1/2 and a negative would be a positive 1/2 cosecant squared x, which is that term. And then a negative cosecant x cotangent x, which is that term. So we've got our answer. So sometimes it's good just to stop here in a second and then just take a break. And it's really weird when you have to switch your mind back to, okay, now derivatives. So the more you can kind of find the antiderivative and then go flip side and actually check your answer, the better it's going to be, because otherwise sometimes when you do nothing but antiderivatives and then you go and all of a sudden I give you a derivative, you're like, what? Okay, wait, what's that formula again? You have to really, really think. It's a good challenge to practice going both directions. Trust me. I've been there several times. Okay, so part F. We have the integral of 2 cosine 2x minus 3 sine 3x. Okay, let's go piece by piece. So the indefinite integral, let's pull off 2. And now we want to focus on finding the integral of cosine 2x. Well, the integral of cosine is just 1 over the number attached to your angle, so 1/2 sine of kx. Okay, let's pull off the 3, and the integral of sine is a -1 over the number attached, which is 3, and then cosine of that same angle, and then plus c. So our indefinite integral, 2 times 1/2 goes away, so it'll be sine of 2x, 3 and -1/3, so it'll be plus cosine of 3x plus c. There's our answer right there. I don't know, this looks pretty nice. Let's just check it. Let's take the derivative of this antiderivative. So the derivative of sine is definitely cosine of 2x, but then times the derivative of the angle, which is 2, plus, now the derivative of cosine is negative sine 3x times the derivative of that angle, which is 3. So going back up, this would be 2 cosine 2x, which checks out with the first term, a minus, so that'd be minus 3 sine 3x, and that checks out with the second term. So we did good. Okay, part G. We have 2 terms in here, so we want to go find the antiderivative. We'll go piece by piece. Well, the antiderivative of any constant, all you do is just add the variable x to it. So it'll be just like 1 times x, or I'm just going to put an x. Okay, and then the integral of cotangent squared. Well, if you go to your list, hopefully you're looking at going, oh wait, we don't have an antiderivative for cotangent squared x. So what are we going to do? We've basically got a big question mark sitting right here. What that means then is we have to go back and manipulate our function before we can take the integral. Because if we don't have a rule to take any integral of any part of it, then we really can't go further with it. We have to go back and play around with it. Okay, so I'm going to go back to our wonderful glory days of trig. And we had this wonderful formula, like, the sine squared plus cosine squared equals 1. Well, another version of that is 1 plus cotangent squared x is equal to cosecant squared x. Or you can say then that cotangent squared x is equal to cosecant squared x minus 1. Let's go in there and make that substitution then. So now we're looking at the integral of 1 minus, and then if I plug in what I'm substituting for, it'd be cosecant squared x minus 1. Okay, put that in parentheses and then dx. So combining some like terms, then really what we're looking at is the integral, let's see, of 1 plus 1, which is 2, minus cosecant squared x dx. Okay, so now do we have a formula for cosecant squared x as far as taking the antiderivative? We sure do. So now we can work from there. But I kind of wanted to show you that when you get to that step, you're like, ooh, do I just you can't just make stuff up. It'd be kind of fun, but we got to keep working with it and just go back to kind of using some of your identities. There's a reason why they tortured them with us in pre-cal and trig. Okay, so term by term. The integral of 2, anytime you have a constant, you just throw the variable with it, so it'd be 2x minus, and then the integral of cosecant is 1 over, it's negative 1 over the angle, that's any number that's attached to the angle, in this case is still 1, and then it's going to be cotangent of that angle, and then, as always, plus c. So combining what little I can, it looks like it's going to be plus cotangent of x plus c. Okay, so that would be our answer. And just know that if you had to go back and actually check this one, because we made a substitution, if I go through and take the derivative of each piece here, the derivative of 2x is 2, and if you go back to your main function, we don't have that, so we got to go back to a substitution. So really when you check, you want to go back to this step where you made the substitution. So the derivative of 2x is 2, and the derivative of cotangent x is a negative cosecant squared x, which would give you that one, and so then it would check out. All right, example 3. We want to verify for sure that by the time I take the integral of this left side, I actually get to this right side. Okay. So what you're seeing here on the right side is our antiderivative. This is our f of x. So the way I'm going to verify is I'm actually going to take the derivative of our antiderivative. Okay, so I want to take the derivative. Let's write it as, actually, let me come up here just for 1 second. I'm going to rewrite the function just a little bit of the antiderivative. I want to write it as negative 1/3 3x plus 5 to the negative 1. Okay, so now in that form, I'm going to go through and find the antiderivative. Or I'm going to take the derivative of this antiderivative. Okay, we would normally just pull that constant out front, and then let's just focus on this part right here. We would drop that exponent down front, keep the base the way it is, subtract 1 from the exponent, and then multiply by the derivative of the base, which is 3, and then the derivative of c is 0. Okay. So the derivative of the antiderivative, you can get it tongue-tied that way, by the way, but yes, it's 1/3 times 3x plus 5 to the negative 2. And also we have, the 3 in the back, I forgot about that. So this 3 in the back is going to cancel with the 1/3 in the front. So right now it's looking like just 3x plus 5 to the negative 2. And since we could either write it like that, which obviously is exactly where we were right there, or if you want it with a positive exponent, obviously it would be 1 over 3x plus 5 squared. But we got there. It checks off. All right, let's do that process again. We want to verify that on the left we do, by the time we take the integral of this left side, we're going to get the right side. So again, this right here is technically our potential antiderivative. Okay, like I started before, let me clean this up just a little bit. That angle is really what I want to clean up. I don't like that, the way it's written. So it's not as recognizable. So f of x technically is negative 3 cotangent. I'm going to write that as 1/3 x minus 1/3 and then plus c. So now we're going to take the derivative of this and hope that by the time I'm done with the derivative, I've got this thing sitting right there. So f prime, let's pull off the negative 3. And what is the derivative of cotangent? Well, the derivative of cotangent is the negative cosecant squared. So it's going to be negative cosecant squared of that angle and then times the derivative of that angle. So it's just times 1/3. And obviously the derivative of c is 0. Okay, f prime of x is equal to, and do a better job of cleaning this up at one time, a negative times a negative will go away. The 3 and the 1/3 out back will go away. So we just have cosecant squared of our angle. And if we wanted to, we could put that back together in that form how it was, but it checks off and we are good to go. Example 5. We want to solve dy dx equals 9x squared minus 4x plus 5, where y of negative 1 equals 0. Okay, so what it's asking us to do is basically to go backwards. We want to find the original function. Okay, so we're finding the integral of dy dx, which is going to be the integral of this whole side, 9x squared minus 4x plus 5. Okay, well, the integral, or I guess if you want to write it in the sense of this notation, the integral of dy and then the integral of the 9x squared minus 4x plus 5 dx. And that's the notation we're used to really seeing right there. Well, the integral of dy is just y, and then we're going to take the integral of each of these piece by piece by piece. So let's pull off the 9, x to the plus 1 over the new exponent, minus 4. Okay, 1 plus 1 would be 2 over its new exponent, and then plus 5x, and of course we always have to add plus c. So cleaning this up, we get y is equal to 3x cubed minus 2x squared plus 5x plus c. Now, this is where we're going to pull this last little piece of information. It says when I plug negative 1 into my function, what comes out is a y value of 0. So 0 is equal to 3 times negative 1 cubed minus 2 times negative 1 squared plus 5 times negative 1 and then plus c. So the whole reason why we're using this piece of information right there is just to find what c is. So 0 is going to equal negative 3 minus 2 minus 5 plus c. So negative 10 plus c, so c is equal to 10. So combining this together into one big function, this will be our answer. So 3x cubed minus 2x squared plus 5x plus 10. And notice how, in order for me to give an example, I had to have a specific point in order to find exactly what c was.